Good day to everyone. So in the last video we have seen about the relation between the angle of shear and the linear strain with an example problem. So in this video we are going to see about what is the work done against a strain. Suppose if you have any physical body, so suppose if you are applying a force on it, then there is a strain will happen. Suppose if you remove the force, then the body is trying to deform to the original shape. So to do that, there is a work is going to be done in this body. So this work done is actually stored in the body as a potential energy. Okay. So what we are going to do is we are going to show that this work done is actually equal to the work done. Then is equal to the half times of stress into strain. Okay, so this work done is actually stored in a potential energy, and this potential energy is actually equivalent to the half the times of stress into strain. This is what we have to prove. So this strain is actually, suppose if you are considering any form of strain, whether it's a linear strain or a shear strain or a bulk strain, so all these kind of strains, this work done is actually same of this form. Okay, so first we have to see about the linear strain. First is the linear strain. To find out the work done to the linear strain, we are going to assume the same experiment where we have a rod of uniform length, uniform area, which is actually the top end is actually fixed with the ceiling, and I am going to apply a force, downward force, so that the rod will be elongated. So originally the rod is having the value, that means the length of capital L, and it and the area of cross section is A, and due to this force applied on this wire, there is a change in length. There is an increase in length, which is taken as a small l. So I can write as the change in length can be taken as a L plus small l. Okay. So previously I have taken it as a delta L. So for this, the mathematical convenient, I have taken as the notion as a small l. Okay. Fine. So I know this total length is capital L, and the area is capital A, and the force acting on the wire is actually capital F, and the increase in length can be written as small l. Okay. So using this, I can easily find out what is the work done. So I know that the Young's modulus which is E, which is equal to FL divided by A into small l, the delta L, but here I can get a small l, or I can find out the force. F is equal to E into A small l divided by capital L. So I know this force acting on the this is the force acting on the body to make this deformation. Suppose if I remove this force, there is a work is going to be done to produce a stretching. So the work done in producing a stretching, which is equal to, let us take it as a small dl. Dl is a small work done, a small deviation in length. So for this, if you want to do that, then you have to apply a force of F into dl. Okay. So to make this a small deviation, small stretching, you have to do the force. You have to apply a force of F into d times of dl, F times of dl. So I know the value of force, that is nothing but the E A L divided by L into dl. So this is the work done to make the small deviation, that is a small stretching. Suppose if I want to make a total work done, so the total work done to produce stretching of the wire from 0 to L, so that I can take this same formula and I can integrate with the limits of 0 to L. So that is my work done, W, which is equal to the integration of 0 to L F into dl. I know the values of F and dl, so I can just easily substitute here 0 to L EA L divided by L with the dl. So here we can know that this EA, L and L are constants, only the dl is going to be integrated, so that I can take the EA L divided by L as outside, and suppose if I take the deviation, I mean take the derivative integration of this, I can get the L squared by 2 with the limits of 0 to L. Again, if you substitute the values of L, you can get the L squared by 2, and suppose if you apply, substitute the lowest limit, then you get the 0. So the answer is L squared by 2, which I can write as 1 by 2 times of you have to take this L into dl for the integration, so that you will get the L squared divided by 2. You will get the dl L into dl, you get the L squared by 2 with the limitation of 0 to L. So if you apply the value with the upper limit and lower limit, then you will get the value of half E A L squared divided by the capital L. So that is nothing but you can write this as, that is the total work done, W is equal to half E A L small l into L into the small l. So you can write this as half of, this is already you know that E A L into the divided by L is nothing but the force acting on this from the forcing on acting on the wire. So I can write this as half into F into L, so that the total work done is nothing but the W, which is equal to half the times of, that means the stretching force divided into the elongation produced. So which is nothing but this is the total work done. So suppose if you take the total volume of the wire is taken as A times of L, so I can take this total volume of the wire, which is nothing but the A times of L. Then I can find out the total work done per unit volume. Work done per unit volume of the wire can be written as, so the work done per unit volume, which is equal to half times of F into L divided by the unit volume, which is nothing but A into L, so that I can write it as a half F divided by A into small l divided by, this is a small l into L, that is nothing but the half of F by A is nothing but the stress, that means and L into L, that means that the change in volume delta L divided by capital is nothing but the strain. So we can write this work done is equal to half the times of stress into strain, which is what we have previously stated, that the work done is nothing but the half the times of stress into strain, which is we have proved here. So this is the linear work done on the linear strain. So similarly, you can easily find out the shearing strain and the volume strain. So the second one is the shearing strain. So again, I have a same example where I can take the square, which is having a sides of A, B, C, and D. Suppose if I apply a tangential force, then there is a reshape is happening. The reshaped object is actually a parallelogram type. Then with the angle of shear as phi, and the A prime and B prime. So the A prime and B prime again taken as a small l. Okay, so the tangential force is F is actually applied, and the direction of the square. So you can, so this the each and every side is having the value of AB, which is equal to L, and similarly AD is or AB, AC, and DC, BC, everything is having the uniform length, and A prime, that is a change in length, is taken as a small l. So the stress is actually already we know that stress is equal to F by A. Here the unit the area of cross section, the area of cross section is nothing but the AL squared. So I can write this as a AF divided by capital L squared, and the strain, which is equal to that means the phi, which is equal to the change in length divided by the total length. Okay, so I can write the rigidity modulus G is equal to F divided by L into small l, isn't it? Because the originally it's actually have F divided by L squared divided by L into L. So I can write the G, I can get the rigidity modulus G is equal to F divided by L into L, or the force can be find out from the usage G times of capital L into small l. So this is the force acting on the this is relation between the force and the stress and strain. So from this I can easily calculate the work done. So work done to displace the layer AB by a small length dl, which is actually taken as dl, which is equal to F times of dl. Again, I know the F value here, so GL into L dl. So that is my dl value. And suppose if I want to find out the total work, so I have to find out the total work. I can take it from the value with the limit from 0 to L. I can easily integrate this equation with the limits of 0 to L into F into dl. I know the value of F and F, so that I can easily substitute here G capital L into dl. So again, the GL is a constant. I can take it outside. So L into dl is the we want to integrate, so that I will get the L squared divided by 2. So, and if you apply a limit, I can get half half G capital L squared. So this is the total work done. Again, I can write it as half G capital L into L, so that I can write it as a half F into L. So nothing but the half of the tangential force multiplied by the displacement. Okay, so that is the total work done. Suppose if you consider this as the three-dimensional object, suppose if you consider this as three-dimensional object, then you can find out the volume. This volume is nothing but the L cube. So I can write the volume of the cube is V cube. So I can easily find out the work done per unit volume. Work done per unit volume is nothing but the half F small l divided by L cube. This is not a B cube, it's actually L cube. So V is equal to L cube. So that I have a work done per unit volume is equal to half into FL divided by L cube. I can write this as half F divided by L squared into small l divided by capital L. Again, you can just for the mathematical simplification, I can write this as this. So this again the F divided by L squared, I can write this as F by A because the L squared is nothing but the unit per area of cross section. So I can write as F divided by A into the L divided by L. The small l delta L by L is nothing but the angle of shear. So I can write as a phi. So which is again is proved as F by A is a strain into the stress. Sorry, F by A is a stress into the angle of shearing angle. So this is strain. Again, it's proved that the total work done per unit volume is actually equal to the half the time of stress and strain. So similarly, you can find out this. You can prove that the volume strain is also actually having the same form. So the third one is the volume strain. So this volume strain is actually happening when suppose if you have a object and you are applying a force on the each and every direction. Sorry, I just forget to totally tell this difference between the linear strain and shearing strain and volume strain. So once suppose if you are applying here, suppose if you have a cylinder like structure, that means a wire, this form. Suppose if you are applying a force in this direction, that means in the is just parallel to the force, then this cylinder will get the change in the length, elongation. That means you get the change in length is happening. Suppose if you are applying a force in this direction, this is the first force one, and if you are applying a force in the tangential direction, then the shape will be changed. It will be like this. That as we previously see in the previous example, so that you can find out the angle of shear. Or sometimes suppose if you have a same cylinder and you are applying a force, that means suppose if you have the top view of the cylinder is actually shown here, and the load is actually applied, the force is applied in all the direction of the angle, the wire or a cylinder. Then the first one where the force is used to increase the length is called the linear stress, and suppose the second force, which is actually perpendicular to the axis, is actually in the shear strain, and the force which is actually acting on all the directions of the cylinder is called the volume strain. Okay, so we are going to find out such case as volume strain. So in this case, we are not actually applying a single force, but we are actually applying the whole different forces, different equal forces on all the sides of the cylinder or a body, so that which we can take it as a pressure. Okay, so this pressure is taken as a P, and it is actually uniformly over the whole body. And so suppose if you consider the V is the volume, volume of the body, and suppose due to this pressure there is a change in the volume, so that I can write this the small v is the change in volume. Okay, suppose due to the pressure, once if you apply a whole pressure, so that there is a change in the volume. So that is actually changed to V. Therefore, I can write the bulk modulus K is equal to the total pressure divided by the change in the volume with the total volume, or I can write the P is equal to K times of V divided by capital V. So this is the force. So again, we know the force between the pressure, then we can easily find out what is the work done to produce a small decrease in volume, that is dV, which is nothing but the P times of dV. I already know the value of P here, so that I can easily find out so the total work done for the whole decrease of the volume, decrease of volume from 0 to small v, I can write as W is equal to, again, the integration of 0 to small v, P times of dV. Again, I can know the value of P from here. I can directly substitute here 0 to kV divided by capital V into dV, which is actually similar like the previous steps. So we will get the half of kV divided by V, that means called V squared by 2 you will get, so that I can write it as a half kV V squared by V, or I can again write it as half of kV divided by V into V, so that this can be written as half of P times of V. The stress into that is half of stress into change in volume. So this is again the work done in the So you can easily find out the work done per unit volume. Which is nothing but the half of P small v divided by V, or I can write it as half P times of V divided by V. The P is the stress, and the change in volume divided by total volume is the strain. So again, I proved that the work done per unit volume is equal to the half the times of stress and strain in the volume and in the volume strain also. So in all the three strains, that means the linear strain and the shearing strain as well as the volume strain, the relation between the work done is actually saved as the the work done is actually equal to the half the stress into strain. Okay. So I stop here. This video is actually, we stop this video here, and we see the couple of problems in the next class. Thank you. And if you have any doubts, then we can, as usual, discuss in the online class. Thank you.